I thought I'd make another video on using these STC microcontrollers. This is the same circuit I used in my Hello World video that I did last. This time we're going to use one of these IR receiver modules to receive IR remote commands. These will be Sony 12-bit remote commands, and we'll turn this LED on and off with it. We won't be using any interrupts or libraries or anything like that. It'll be pretty simple code that I'll explain. First of all, let's demonstrate it. I have it set up so when the remote sends out a TV code of 1, it will turn the LED off, and 0 will turn the LED on. That might seem backwards to you, but actually it's just putting a 1 or a 0 on the port pin and turning the LED on and off. That's why I did it that way. This works from way across the room too, so it's not just it doesn't have to be 2 inches away. I'm powering it from a power bank. This is the serial converter I was using before, but it's not hooked to a computer now. This is just a method to get power into it. This is one of those cheap infrared receiver modules you buy from Banggood or places like that. I'll show the circuitry on it now. It's the same basic schematic as I had on the last video. Only difference is I've hooked the LED up so that when you apply ground to it, it turns on instead of the way it was before, because this will be a little brighter. Here's the IR receiver. One pin goes to ground, one to VCC, and the other pin goes to port 32 on the microcontroller. This push button is not used. This is the switch and this are part of the programming circuitry. Now I'll show a little about the Sony IR commands. Before we go to the computer and look at the code, I'll explain the signal we're going to be decoding. It is a Sony 12-bit signal where our address bits, there are 5 address bits, 7 command bits. The command is like the key, the 0 or the 1. The address is like the device, so if a VCR and a TV will have different addresses. This IR receiver puts out a low in the presence of a carrier signal. So the carrier signal in this case is 40 kilohertz. So every time it sees this 40 kilohertz signal, it puts out this low for that period that the signal is on. The Sony commands start with a 2400 microsecond burst of 40 kilohertz, which gives you a 2400 microsecond low signal. The ones and the zeros are determined by the length of the next 12 low pulses that are output. A 1200 microsecond low period will be a 1, and a 600 will be a 0. This high here is when the carrier frequency is not being transmitted. It is 600 microseconds, and it defines, or it separates the bits. Our program will not be looking at this 600 microsecond high at all. All we're going to do is we're going to wait for the 2400 microsecond start pulse, then we're going to count the next 12 pulses, and if they are not count, we're going to shift them in. If they are more than a certain threshold, I believe it's 900 microseconds, it will be considered a 1. Otherwise, the bit will be considered a 0. This is a simple way of doing it, definitely not bulletproof. You can see this signal, they're pretty easy to decode just by eye. This is the least significant bit. This is the most significant bit of a command. This is the least significant bit. This is the most significant bit of the address. So a long is a 1, a short is a 0. So 110010000, and the address is 11010. These are in there. If you look down here, I have them written out. So this address, this is the most significant bit, 01011, and here is our command over here. This signal actually interpreted. So 1 is the least significant bit, 001, 000. There's 7 bits and 5 bits. This, when you look at the 1417, when you look at the bits as an unsigned integer, which is what the program does, this is the value you have. When you break it down into the 2 bytes, or not bytes really, 7-bit command and 5-bit address, these are the values you get. This was for, I have this universal remote set up for a VCR or a TV. This was this bit pattern is for a VCR with the 0 button pressed. If this is a different one, it's a VCR with the 1 button pressed. You can see the start bit, and the command is actually 0, so it's not near as interesting as the last one. So to read it, all we have to do is read the length of the low pulses. So 0, 0, 0, 0, 0, 0, 0, and then we have a 1, 1, 0, 1, 0, and that what I just read off is this in reverse order. The command, all zeros, and the address, which is actually decimal 11. We'll do that in code. We'll go to the computer in just a minute and I'll show how it's done. Here we are back in the STC-ISP software. We're going to use its built-in terminal program, the COM helper, to display some output from our board that we have plugged in over here when we send it commands with this remote. First of all, we're at 2400 baud, which is what it's expecting. The COM port is open. Let's send it some commands. We're in TV mode on the remote. Let's send it a 0 to turn the LED on. It's on. Let's send a 1 to turn it off. Okay, it's off. Now let's change to VCR mode. Let's try to turn it on with a 0. It doesn't work. Or turn it off with a 0, either one. Let's clear this out. Put the remote back in TV mode. I'm just pressing the TV button. Clear that out again. Now let's turn the LED on by sending a 0 to it. And look at what we've got up here. First of all, 137 is the unsigned integer, but the 12 bits are held in a 16-bit unsigned integer in the program. A equals 1 is the address. C equals 9 is the command. So command is 9, address is 1. Let's send it a 1. I got 2 of them out of it because I wasn't off the button fast enough. It repeats very fast. So when we press the 1 button, we got all the bits added up together are 128 in the unsigned integer. The address is 1. Now the command is 0. Let's look at these binary numbers. They represent this 128 or this 137 in this case up here. Let's look at the top one, 137. The way that the Sony commands are encoded is if we start counting from the right over here where our cursor is, 7 bits, we'll come to right here. Everything to the right of a cursor now is the command. Everything to the left is the address. So let's 1, 2, 4, 8. 8 plus 1 are the set bits, so that's a command of 9. And the only address bit we have set is 1. So that equals 1. Address equals 1. Command equals 9. Let's go down here and look at the next one. 128. If we count over from all the way to the right, count 7 bits to the cursor there. Everything to the right of that cursor is a 0, so our command is 0. And again, we have the same address as we had before, 1. Let's put it in a different, put the remote in VCR mode, and that'll send out, let's clear all this out. Now we'll send a 1. We have 2 of them here. 1408 is all of these bits together in an unsigned character. So we count over from the rightmost bit 7 times. Those 7 bits are 0. The command is 0. Now we look at starting here at this is the 1 bit, the 2 bit, 4, 8. So 8, 2 and 1 are set. 8 plus 2 is 10, plus 1 is 11. That's our address. Same thing down here. This is the same command. Now I'll send it, forgot what I sent it before. Yeah, let's send it a 0. This down here is a 0, 1417. If we move our cursor over, all these 7 bits represent the command. So 1 plus 2 plus 4 plus 8, or 1 plus 8 is 9. And then our address is the same as before. 1 plus 2 plus 8, so that's 11. I think I'm doing my math right. But it'll receive all the codes that we send over remote. I'm going to use these up-down keys now. Here's the up key, the down key. This is in VCR mode because it's address 11. You can see the up key was 66, the down key was 67, left key's 98, right key's 97, channel up is a 17. No, that was channel down. Channel up is 16. Mute still back is for the TV, so you can see that right there that it's a TV code coming out as address equals 1, command equals 20. So that's pretty much how we're decoded. Let's go into the software and take a look at what's going on. Here we are in Notepad Plus with the code opened up. I'll do a short walkthrough of it. We have some comments at the top. This include my stc.h is the header file. It needs to be in the same directory as the source file we're looking at right now. These are the defines for the port pins. The LEDs on port 3.3. The transmit line for the software serial port is port 3.1. The IR receiver pin that we're going to receive our signals through is port 3.2. The start min and start max are limits for the length of what we will consider a valid start pulse. The logic 1 is the low limit for what we will consider a 1 logic or a 1 pulse. It's the low length of the pulse. Some function prototypes. The part of the program that decodes the signals is these 2 routines right here, or functions. Get pulse length just gets the length of a pulse, a low pulse on the IR receive pin. The way this works, we're not going to use any interrupts, but we are going to use a timer 0 in 16-bit mode, which is what it starts up in, so we don't even have to set it up. In this mode, at a 12 megahertz clock frequency, the 12 megahertz gets divided by 12 to produce a 1 megahertz clock for the timer. So each timer tick will equal 1 microsecond. These timer high and low are where the timer value is stored. TF0 is the overflow flag when it rolls over from all ones to 0. I don't really think we need to mess with that, but I just did that for whatever reason. Timer 0 or TR0 is tells the timer to run when you put a 1 in it, and it stops the timer when you put a 0 in it. To measure the length, what we're going to do, we want to measure this low length here, but the program doesn't know where it's going to be called from. So if it gets called in the middle of a low length, we want it to wait till the pin is high again. So while not IR receive, if line is already low, wait until it's high. It'll sit here and just wait till it goes back high. It'll sit here forever. And then we want to wait after we know we're on a high level. We want to wait till the pin drops low. So that brings us here while IR receive. So if it's high, it's just going to sit here. When it goes low, it'll fall through here where we'll reset the timer to 0 and then start it running. Think of it as a stopwatch. We just started the stopwatch. Now we want to wait till it goes back high again right here. So while not IR receive, wait for line to go high. When it does that, we stop the timer and we return this function, returns the value, an unsigned integer, timer low plus timer high, shifted right 8. So it's just a 16-bit value representing the timer. This routine, it's called many times by this routine, get IR code. What it does, first of all, we're going to stop in this loop right here. We're just going to set in this loop until pulse length equals get low pulse length. Well, we're going to stop in this loop right here until we get a pulse length, and then we compare it to make sure it's greater than start min and less than start max. So we'll set right here as long as this pulse length is outside of these limits. It'll just sit here waiting for a valid start length for the pulse. After that, we're going to shift in 12 bits for state equals 0 to 12, so it amounts to 0 to 11 for the shift function. We're going to get a pulse length by calling this routine, and if pulse length is greater than logic 1, we're going to set that bit in the bit pattern to a 1. So bit pattern equals bit pattern or 1 shifted right state. So every time through here, state's going to increase, and this just depends where it's going to set where this 1 bit gets put into bit pattern at. If to do a 0, it's just assumed that the bit will be a 0. That's why we reset bit pattern to 0 up here. And this function just returns bit pattern. What it's going to return is an unsigned integer that's equal to the 12 bits of the Sony IR code, even though this is 16 bits long. This setcom address or sendcom address just sends out the Sony code as both an address and a command. And here's other functions to get the address and get the command. It just breaks the 12 bits down into the command and the addresses. These unsigned characters are casting. You have to, one of the things with C is you have a 16-bit variable and you want to do something with it and end up with an 8-bit result. You have to be very careful, and that's what this does. It casts this result as a 8-bit unsigned number. It gets very confusing. Most of the rest of the program is just a continuation of the last video I did where we made all these routines that print out numbers and things for Hello World video. Here's the main part of a program. It just defines some variables, sends out a hi message at the start. I didn't even show that when I had it on the COM port, just to let you know that thing's alive. If you want to know if your program is working when you're in that COM program, clear the screen and push cycle the power, and it'll send out this hi message at the start. Down here in the forever while loop, it's going to IR value equals IR get code. We're going to call that function up top that gets the code and put the resultant IR value. And we're going to send it out with a line feed, send it out as a binary number with a line feed, then break it down as its command and address. That's what all those printouts were we were looking at before. This is the part that does the LED on and off. If the command value equals 0 and the address value equals 1, that's key 1 on the TV setting I had before. Then turn LED equals 1. A 1 will turn the LED off because the cathode is hooked up to ground and the anode is hooked up to the pin. And down here, if the command value equals 9, which is the key 0, I know that's strange, and the address value equals 1, the TV address, then LED equals 0, or turn it on. I had it printing out report stuff and things before, but that got kind of confusing. That's the basic run through of the program. This method I've used for decoding it's not mine. I've seen it for 20 years. I saw it used with a basic stamp to decode the Sony codes 20 years ago, so I'm not taking credit for it or anything like that. I hope this helps somebody. There's not a lot of content out there for these STC microcontrollers, so I thought I would make some. Well, thanks for watching. Well, I guess I should show how to compile it before I leave. So this is the program. It's already been saved. I didn't make any changes to it. Let's go down to our where we have it stored. I have it stored in my documents, SDCC, in its own folder called Sony No Interrupts. Here's the C file we were looking at. Here's the my STC header file that has to be in this directory. Let's take a look at this batch file, which will compile it. It's pretty simple, just 2 lines. The last line just pauses the screen so that the command screen doesn't close before we can figure out what happened. It just compiles the code into this IXH file and then converts that file into a hex file that the STC software can use. So let's compile it. Open it up. We seem to have success generating code, calling assembler. I'm not sure what all that is. Calling the linker. And then this line down here is where it does the conversion of the hex file. Seems to have all worked. A mem file is just created. Let's look at it. And we've used 1144 bytes of its memory. Most of this program is just stuff for printing out the serial port. If you were making this program for real, where you just wanted to control something with an infrared controller, you would, when you got done with all your debugging and stuff, you would get rid of all this serial stuff, which slows the program down considerably. But it certainly helps you debug it. So that's the end.